This video is on Yolo, which stands for You Only Look Once. And with this, we are now getting into one-stage methods of object detection in our series. In this one, we go over how Yolo performs object detection, specifically Yolo1, diving deep into various aspects of the detection process. We'll understand the architecture used by the authors, as well as focus on the multi-part loss used for training Yolo. And finally implement Yolo1 from scratch in PyTorch and train it on VOC dataset. So let's get started. Up till now, in our object detection series, we have only covered RCNN variants, which are two-stage object detection models. Let's revisit the distinction between two-stage and one-stage models that we had seen in our RCNN video. Two-stage detection systems model object detection as first proposing candidate regions which potentially contain an object, and then in stage 2, classifying these regions with the appropriate category as well as regressing boxes of proposed regions to tightly fit the underlying object. An example would be faster RCNN, where we had RPN for stage 1 and fast RCNN detection head for stage 2. In one-stage models, we skip the proposal generation step altogether. And rather than having two separate parts of detection system, there is a single model which directly predicts the boxes and classes from the input image. This reduces the complexity of the detection pipeline that exists in two-stage models, where both these stages have to be trained and tuned. And because of this streamlined detection process, stage 1 models are also faster. But the trade-off is that they end up being less accurate than two-stage models. As part of this series, we'll go over quite a few one-stage models, and the first one of those is Yolo. Yolo models object detection as a single-stage regression problem. The input image is passed to a single CNN. This CNN model extracts features from the image and finally predicts bounding boxes for the detected objects and class probabilities for these boxes. So let's look at everything that's happening within this single model. Yolo creates S cross S grid cells covering the entire image. In this example, we have 3 cross 3 grid cells, but in the actual implementation, the authors use S equals 7. For training, every target object is assigned to only one grid cell. This is the grid cell that contains the center of the target object. So in this image, we have two objects, person and car. The person object has this ground truth box, from which roughly we get this center. Similarly, from the car's ground truth box, we have this as its center. This means that we'll assign person to this 6th grid cell, because the center of the person lies in that grid cell, and the car's ground truth target box will be assigned to the 5th grid cell. For each of these grid cells, Yolo predicts B bounding boxes. And again here, for ease of visualization, I assume B equals 1. But in the implementation, the authors use B equals 2. During training, Yolo learns to have predictions for boxes of each cell as close to the target box that is assigned to that cell, if any. So in this image, for the cells which had targets assigned, we got these two prediction boxes. And through training, Yolo will learn to have these predictions as close to the ground truth boxes. The way Yolo predicts a box is different from what we have seen so far. So let's take a closer look at the exact values that are present in these box predictions. And for now, let's keep only this single box prediction, which was the box prediction for the center grid cell. Yolo predicts 5 parameters for each of the boxes. 2 of those are the width and height of boxes, but these are relative to the image width and height, normalized between 0 and 1. So a width of 1 means the width of the predicted box is same as that of image. For the center of the box, Yolo actually predicts the offset of center from the top left corner of the grid cell that the predicted box belongs to. Now for this predicted blue box, roughly this is the center. And the grid cell that the box belongs to is the green colored cell. Hence Yolo will predict these XY offset values from the top left corner of this grid cell. These offset targets will also be normalized between 0 and 1. So for the same width and height, if the values of X and Y offsets are 0 and 1, that means the center is right here, at the bottom left corner of the grid cell. And if it's 1, 1, then that means that the center is right here, at the bottom right corner of the grid cell. Apart from the X offset, Y offset, and width and height values, Yolo also predicts a confidence score for each box. This confidence score attempts to capture two aspects. How confident is the model that there indeed is an object within this box? And second, how good a fit does the model think that the predicted box is for the object that the box contains? We'll see how we set the target confidence scores so that it captures both these notions later. But for now, just assume this score gives a sense of model's estimate of how good the predicted box is. If we look at the prediction values at grid cell level, then each box has 5 prediction values. And each grid cell predicts B bounding boxes. That means each grid cell will predict 5 B values. Apart from bounding box predictions, for each grid cell, Yolo also predicts one set of class conditional probabilities. So that means as many more values as there are number of classes. Specifically, these values are probability that a class exists in that grid cell, conditioned on the fact that there is an object contained by that grid cell. So we'll have 5B plus C values for each grid cell. And for our VOC dataset, we have 20 foreground classes and the value of B will be 2. Which means for each of the S cross S grid cells, we'll be predicting 30 values. 10 values for the 2 bounding box predictions and 20 class conditional probabilities. Couple of interesting points regarding these predictions. One thing you can see is that even though Yolo predicts multiple boxes per grid cell, but when it comes to class probabilities, it only predicts a single set of class probabilities, no matter what the value of B is. That means each grid cell will only predict one type of object. Secondly, if for each grid cell, Yolo predicts multiple boxes, then given a target associated with that grid cell, do we train both the boxes to match the target box? And if not, then how do we choose? So let's say we have these 2 box predictions and this target ground truth box for that cell. During training, the authors only have one out of all the B predicted boxes as responsible for predicting the target assigned to that cell, and only that one will be trained to match the target box. The responsible predictor box is the one that has maximum IOU with the ground truth box. So here between these 2 predictor boxes, the larger one has higher IOU. So we'll only train that one to be close to the target box. At the same time, in this image, with the same 2 prediction boxes, it will be the smaller predictor box that will be assigned to the target and optimized, and the larger one will be ignored as far as being responsible for predicting this car is concerned. What this selection of only the highest IOU predictor box is going to do is that different predictors will specialize in predicting targets of different size, different aspect ratio, and so on. With an overview of the detection process done, let's look at the architecture that the authors use for the CNN that generates these grid predictions. During implementation, we'll again get back to grid cells, predictor boxes, and target assignment, which will make things more clear. For now, just keep in mind that Yolo divides the image in grid cells and makes multiple box predictions for each of those grid cells. Given an image, the CNN used by authors generates an output with S times 5B plus C values for the entire image. This is ultimately transformed into a S cross S grid with 5B plus C channels. This will be the 5B plus C predictions for all the grid cells of our image. So in our example case of 3 cross 3 grid cells, if the number of boxes per grid cell is 2 and the number of classes C is 20, this CNN will return prediction values that can be transformed into a 3 cross 3 grid output with 30 channels. And each output cell will represent the prediction values for that grid cell. Like these will be the B box predictions and class conditional probabilities for the first grid cell. And likewise the other output cells will be the B box predictions and class probabilities for their respective input image grid cells. For the model, the authors use the GoogleNet network. But instead of the inception module present in GoogleNet, they replace it with 1 cross 1 and 3 cross 3 convolution layers. The authors first pre-trained this network on ImageNet classification task by stacking FC layers and training on image sizes of 2 to 4 cross 2 to 4. Post that, they get rid of the FC layers and add additional convolution layers prior to detection training, specifically 4 convolution layers. After these convolution layers, we have 2 FC layers to finally predict our S times 5B plus C dimensional tensor of prediction values, which can be reshaped to create our S cross S grid outputs. With these changes, we get this architecture as the final detection network. The authors fine-tune this network for detection on images of size 448 cross 448. And these are the additional convolution layers added on top of the ImageNet pre-trained network. The model finally returns 7 cross 7 grid output as the authors use S equals 7. And for VOC dataset, each cell will have 30 prediction values. In order to understand how this model is trained to generate detection boxes and probabilities for each grid cell, let's dive into the loss that is used by authors. Just to remind ourselves, in Yolo, any target object is only assigned to one grid cell, the one which contains the center of the object. And out of all the predictor boxes, only one is responsible for this target, the one which has the highest IOU with the ground truth. Like for this instance, the tall and thin predictor will be chosen and updated to be closer to the target. The loss used by authors has 3 components. The first one is localization loss. The responsibility of this is to ensure that the model learns to predict the XY offset and width and height prediction values of the responsible predictor box of a cell closer to the target assigned to that cell. The second is confidence loss, which is meant to train the model to predict correct confidence scores, which is going to capture 2 aspects: presence of an object as well as how good fit the predicted box is. So we want the confidence score to be of high value when the predicted box has a high overlap with the ground truth target, lower value when the box contains an object but does not fit it well, and 0 when the box does not contain any target object, thereby training the model to mimic the same behavior at test time, where there won't be any ground truth available. So it should predict a confidence score that not just indicates presence or absence of an object, but also factors in how good a fit the box is for that underlying object. The third is the classification loss. And remember, we are predicting conditional class probabilities for the grid cell conditioned on the fact that there is an object. So this loss is meant to train the model to predict right probability values, where for cells that contain the object, the model should predict 1 as the value for that class and 0 for the remaining classes. For all the losses, the authors use MSE between the prediction value and the target value. Now let's dive into how each of these components are formulated. Localization loss will obviously cater to X and Y offset and width and height relative to image. So this will just be MSE between predicted values of x, y, width and height and target values of x, y, width and height. And remember, only one out of the B bounding boxes for each cell, the one that has the maximum IOU with the target, is selected here. Instead of MSE between width and height, the authors use square root of these values for computing the localization loss. To understand why, let's take a hypothetical example where all our predicted width and height parameters are off from their target by 0.1. This plot is between the ground truth box widths and MSE loss values. Since our predictions are always off by the same amount, if we compute MSE between predicted width and target width, we'll get constant value always, no matter what the width of boxes are. Specifically, here since prediction values are always off by 0.1, the MSE loss will be 0.01 for all box widths. So what you are effectively telling the model is that whether you make a 0.1 error on a large box of width say 0.9 or on a small box of width say 0.2, you will be penalized the same. But while we might be okay with this 0.1 error on large boxes, the same error is detrimental for small boxes. So this MSE between square root of width and height is a way to teach the model that small deviations on large boxes matter much less than small deviations on small boxes. As once we plot this MSE on square root values of widths, we see that even for the same 0.1 error in widths, MSE between square root of widths will be larger for small boxes and much smaller for larger boxes. Next we move to confidence loss, and this will just be MSE between target confidence scores and predicted confidence scores. And finally our classification loss is just MSE between ground truth class conditional probabilities and target probabilities. Now these objectness and localization losses are just for one box and classification loss is just for one cell. So these need to be summed over all the boxes and cells respectively to get the total loss. For localization loss, we only want to compute this MSE for boxes which are responsible for some target ground truth and ignore the rest. So this sum would be over the predictor boxes of cells assigned with some target that has maximum IOU with the target box. This indicator function exactly filters only those boxes. It would be 1 if the cell I is assigned a target and box J is responsible for that target. For confidence loss, we want to ensure the confidence of these responsible predictor boxes are closer to their target value. But we also want to train the model to predict the confidence scores of boxes which are not assigned to any target object as 0. This second term takes care of that by making use of this indicator function, which is just 1 minus the term that we saw earlier. So this will be 1 for those boxes that are not responsible for any target box. The sum for classification loss, which has class conditional probabilities, needs to be done only for all the cells that are assigned some target, which is done through this term. The final loss is a summation of all these terms. For most of the images, we would only have few cells that would be assigned with some target and a lot of background cells. This would cause the gradient from confidence score of boxes with no objects to overpower those that contain objects. To mitigate this and to weigh localization error higher than classification error, the authors introduced two terms. The first one is to increase the weight of localization error, and the second is to reduce the weight of confidence loss from no object or background boxes. The value of these terms used by authors are 5 and 0.5 respectively. So that's how this multi-part loss is formulated. Before moving on from loss, we need to take a look at few details regarding confidence scores and class probabilities. Our confidence loss was MSE between confidence score predictions and targets. Earlier we talked about how confidence score is meant to capture the confidence of a model that an object exists and how accurate the model thinks that the box fits the underlying object. With this goal, the authors formally define confidence as probability of object times IOU between predicted box and ground truth box. During training, for all no object boxes, the confidence score targets will be 0 as the probability of object is 0. For all the boxes responsible for predicting an object, the confidence score target will be probability of object, which is 1, times the IOU between the responsible box predictor and target ground truth box. So effectively, it will just be the IOU between the predicted and target box, ensuring that our confidence score prediction will be low not just for boxes where the model believes that no object exists, but also for boxes for which the model believes that they don't tightly fit the underlying object. Coming to our class conditional probabilities, these were probability of classes given that an object exists. The detection model ultimately needs to predict class-specific confidence score for each predicted object. But what we have here is a confidence score and a class probability. During testing, the authors predict the class-specific confidence score for each box by multiplying both these terms. This product at test time effectively encodes the probability of that class present in the box and how well the box fits that object. Obviously, at test time, we won't know the IOU between target and prediction, but it will rather be the model's estimate of IOU. With all the components of loss now taken care of, let's quickly summarize the targets for each of these losses and how they are defined. For localization loss, we have seen that given a target box, we identify the cell that the target needs to be assigned to using the center of target box. And out of the B predicted boxes, choose the one that has highest IOU with this target as the responsible predictor for this target box. The coordinates of target box for common datasets will be defined in either x1, y1, x2, y2 or xy coordinates of center and width and height format. But we need to convert this to what the Yolo model expects, which is xy offsets and width and height, normalized between 0 to 1. The target width and height will just be the width and height divided by image width and image height. This will normalize these values from 0 to 1. For the xy offsets computation, let's assume that we are working with x center, y center and width and height format. We need to find the center offset from top left corner of the grid cell. With S grid cells, each cell will be of height and width h by s and w by s. So our grid offset targets will be this. And again, we'll normalize it so that target of 0, 0 represents the top left corner of the grid cell and that of 1, 1 represents the bottom right corner of the grid cell. For assigning targets for confidence scores, we identify the grid cell which have objects assigned, so these two in this image. And for these, from the B predicted boxes, we pick the one that has the highest IOU with the assigned target. And only for these responsible predictor boxes, we'll have whatever is the IOU value as the target. This will be the first term of the confidence loss. For all the remaining boxes, we set a target confidence score of 0. This means even those boxes which belong to grid cells that were assigned an object but weren't chosen to be the responsible predictor. So this is our second term of confidence loss. For the third classification loss, the targets are simple. For grid cell assigned with some target, we have it as a tensor with target class index being 1 and rest all values being 0. So assume we have just two classes in our dataset, person and car. For the grid cell assigned to car, it will have 0, 1 as the target and that assigned with person object will have 1, 0 as the target. And since we only need to worry about cells assigned with some object, this is it. Let's summarize all the important points up till now. Yolo creates S cross S grid cells covering entire image and predicts B bounding boxes for each of those cells. For each of these B bounding boxes, we predict 5 values: width and height of the box, and the x and y offset of the box center from the top left corner of the grid cell that box belongs to. For each of these boxes, we also predict confidence scores, which represent the probability that box contains an object, as well as how good a fit is that box for the object that it contains. Additionally, for each grid cell, we predict class conditional probabilities, which encodes how likely that grid cell contains a particular class, conditioned on the fact that an object center exists in that grid cell. For training, each ground truth object is assigned to one grid cell, the one that contains the target box center. And for each grid cell, Yolo predicts 5B bounding box parameters, and adding the set of class probabilities per cell, we get 5B plus C values per cell. Given a target object and grid cell assigned with that target, during training, out of B predicted bounding boxes, we only choose one predictor to be responsible for predicting the ground truth object, and this is the one with the highest IOU. The final output will be S cross S feature map with 5B plus C channels. During implementation, we'll follow these steps. Pre-train a backbone network with images of size 224 x 224. For this, we'll actually just use a PyTorch pre-trained network. Then get rid of the classification FC layers and add detection layers. Convert the target box locations from XY width and height or X1, Y1, X2, Y2 to Yolo format with XY offsets and width and height normalized between 0 to 1. Implement Yolo loss, which has all the three paths: localization, confidence or objectness, and classification. And train the detection network on resized images of size 448 x 448. We will now go through an implementation of Yolo v1, covering the target formulation, model, and loss implementation. I have created this config, which provides the necessary parameters of the dataset as well as model that we are going to be using. Our training dataset will be VOC 2007 plus VOC 2012 train val images, and test dataset will be VOC 2007 test set. We have 20 classes for VOC, and our data loader will provide us with images resized to 448 x 448 for detection training. For our model, we have the input channels in image, the channels that the backbone returned feature map has, and its spatial size, the channels that the Yolo convolution layers will have, parameters for the FC layers, and finally the grid size, which will be 7, and the number of boxes predicted at each grid cell, which will be 2. The remaining parameters are all related to training. Now let's look at the dataset class, which is VOC dataset. This class first gets everything it needs for fetching the images and creating Yolo targets. Then we define the augmentations which are mentioned in the paper. For augmentations, I use the Implementation library, and for training, we have the horizontal flip, affine, and color jitter augmentations, and a resize to 448 x 448 at the end. For testing, the only augmentation is resizing. After setting the class list for VOC, this method here gets all the images and annotations from the XML files of Pascal dataset. This is similar to the previous video where we implemented faster RCNN on VOC dataset. It gets the image sets that we are going to be working with, and then based on that sets the images and annotation file path accordingly. Then we iterate over all the images and get some metadata for the image as well as all ROIs present in the annotation files. For each image, we create a dictionary in which the detection key has all the ROIs. GetItem method of the dataset class is the one where we have Yolo specific changes. We get the image and bounding box and label information for all the ROIs. But remember, these boxes are in x1, y1, x2, y2 format and they are unnormalized. So we'll have to modify them later, as what we need is boxes parameterized with x and y grid offsets and width and height, all normalized from 0 to 1. Then we apply the augmentation and the library automatically modifies the boxes as well. We normalize the image according to ImageNet normalization, and this is only because we are going to be working with a ResNet 34 backbone that is pre-trained on ImageNet, and that expects this normalization. Now we get to building the target for this item. Our target will just need to be S cross 5 plus C, because we only have one target assignment for a cell. But I still create targets to be S cross 5B plus C, where the 5 values of target X and Y, width and height and confidence scores will be duplicated B times. This is just because my loss implementation expects that way and no other reason. As of now, target is initialized with all zeros. For computing center offset values, we need to know how many pixels are there in one cell, which is this cell pixels. I assume that we'll always work with square images, so this is h divided by s for both the dimensions, along width as well as along height. From here, we start with bounding box format conversion for Yolo. We first get the width and height of the box, which will be x2 minus x1 and y2 minus y1. And coordinates of center Cx and Cy, which will be x1 or y1 plus 0.5 times width or height. At this point, all we have done is just convert x1, y1, x2, y2 format to x center, y center and width and height format. Now from the center coordinates, we identify the grid cell that this box should be assigned to by identifying the cell I, j that contains its center. Cx minus grid cell I times cell pixels will give us the pixel offset from top left corner. And then dividing by cell pixels normalizes it from 0 to 1. Same for y offset. Then we also get the normalized width and height parameters. Our Yolo target, which was initialized with all zeros, will now be updated with all these target bounding box values. And for each target bounding box, we duplicate it to match the 5B box parameters that Yolo is going to predict for every cell. And like I had said, this duplication is not necessary. That's just how my implementation of loss expects. This loop here, given a target bounding box, gets the grid cell I, j value for the cell that this target bounding box is assigned to. And for that, updates the x offset, y offset, width, height, and confidence targets for each of the B predictor boxes. For width and height, we are going to have the model predict the square root of width and height, since anyway we need MSE loss to be computed between square root of these terms. So assuming B equals 2, for a given target box, after this loop, we would have updated the first 10 values of the cell assigned with that target box. Note that as of now, our confidence score target is just 1, but later we'll have to change it to IOU, as this confidence is defined as probability of object times IOU by the authors. Then we get the class label and create a all-zero tensor with 1 only at the class label index. This is set as the last 20 values of the target I, j grid cell that we are working with. Apart from Yolo targets, I have the method also return original bounding box targets. So x1, y1 and x2, y2 normalized from 0 to 1. But this is just for evaluation and visualization. For training, only Yolo targets will be used. Now coming to our model class. We won't be pre-training on ImageNet, but rather take a pre-trained ResNet34 without its classification layers and set that as our backbone for detection training. This is just replacing the GoogleNet model that the authors used with ResNet34. And one can experiment with any other pre-trained model as well here. After the backbone, we'll have the 4 convolution layers for detection that the authors added, and then 2 FC layers. Apart from the last linear layer, all layers will have leaky ReLU activation just like in the paper. The final layer is going to have S times 5B plus C as its output dimension. In the init method, we just get all the values from config. So the default values of image size and channels will be 448 and 3. ResNet34 will give us a feature map with 512 channels. The authors added convolution layers with 1024 channels, which is the default value of this Yolo1 channels. Spatial size, which is the size of the final feature map returned by convolution layers, is 7. And the first FC layer has an output dimension of 4096. All of this is same as what's mentioned in paper. After getting the pre-trained ResNet model, we set the backbone as a sequence of its layers without the FC layers. Then we have 4 convolution layers with batch norm and leaky ReLU activation, with the second one having a stride of 2. The prediction layers are just 2 FC layers with a dropout in between. Given an input image of 3 x 448 x 448, the model's forward method calls the backbone, detection convolution layers, and finally FC layers to return 1470 output values, which is nothing but 7 times 7 times 30. Now we come to the loss implementation, which, just to refresh, should have these 5 components. For loss, I created this Yolo1 loss module, which is going to compute all the loss terms, localization, confidence or objectness, and classification, and return the combined value for Yolo loss. The forward method of this module will receive the prediction which our model's forward method returns, so batch size cross 1470 values, and target, which our dataset class returns, which was batch size cross S cross S cross 5B plus C. In here, we first reshape the prediction tensor to be batch size cross 7 cross 7 cross 30. So same shape as target. For computing both localization and objectness loss, we need to get the responsible predictor box out of the B boxes that each cell predicts. And for that, we need to compute IOU. So the first thing that we are going to do is convert the X grid offset, Y grid offset, and square root of width and height predictions by the model to x1, y1, x2, y2 format, normalized from 0 to 1. And we'll do the same conversion for target. Since the xy values are offsets from top left corner of grid cells, we define shifts for all the grid cell. The cell indexes are 0, 1, all the way to s-1 in both directions, and shift pixel values for these will be cell index times 1 by s. That's because s cells cover the entire image, so s cells equals 1, So one cell is 1 by s pixels. After getting the shifts for all the grid cells, we transform them to be of shape 1 cross s cross s cross b. So the last dimension is for the b boxes at each grid cell. We do similar transformation to the prediction boxes, where from batch size cross s cross 5b plus c, we get the box parameters, so the first 5b values of the last dimension, and then reshape it to be batch size cross s cross b cross 5. For converting the offsets in grid space to offset in image space, we first multiply the prediction by 1 by s. Again, because s cells equals 1. For example, an offset of 0.5 in grid space is offset of 0.5 by s in image space. Then we add to this the shift value, and this gives us the x center. And then we just convert x center to x1 by subtracting 0.5 times width. And remember, since our model predicts square root of width and height, so we have a square here. We do the same computation to get prediction boxes x1, y1, x2, y2. And the exact same for target boxes to get target x1, y1 and x2, y2. Because we duplicated target boxes b times, at this point, both prediction and target boxes are of the same shape, batch size cross s cross b cross 4. Then we get IOU for these set of boxes, which is simply finding the top left coordinates and bottom right coordinates for the intersection box, and then computing intersection area divided by union. Same method that we have been working with in the past videos. From the IOU returned, we get the max along the last dimension. So this will give us the box index out of the b predicted boxes at each cell that has the maximum IOU value with the target. Now this IOU is for the entire set of grid cells. But for localization and objectness, we need indicator functions to give us only cells which have objects assigned and which are the responsible predictor boxes out of the b boxes. So that happens here. We first create the isMax IOU box term, which is going to be 1 for the box index that has maximum IOU and 0 for the other b-1 indexes. To do that, we repeat the last dimension of max IOU index b times, and then also create a box index tensor which is just 0, 1 all the way to b-1, and repeat this also b times. Then wherever these two values are equal, that is the box index which has maximum IOU for that grid cell. So we set 1 for that box index and 0 for all the other box indexes. We also need a cell object indicator term, which will be 1 only for cells assigned with an object. So those cells for which the confidence target as of now is 1. Since we duplicated the target values for each cell b times, so we just get the confidence value for the first box for each cell. If that is 1, it means that this cell is indeed assigned a target. With these two terms defined, we are now ready to compute individual loss terms. First, classification loss. This is just the MSE between class probabilities of target for each cell and predicted probabilities for each cell. But we need to use our object indicator to filter only those terms coming from cells which indeed have been assigned an object. Next is objectness loss for the responsible predictor. This will be MSE between predicted confidence score for the B boxes and target confidence score. For target, notice that we take the maximum IOU value. because that is what the authors use as the target confidence score. But this also should only be applied for cells which have been assigned an object. And for those cells, only the responsible predictor box needs to be used here. So we multiply the object indicator term and isMax IOU box indicator term. Object indicator will filter out all the cells which were not assigned an object, and the isMax IOU box indicator will filter out all boxes which were not the responsible predictor for that cell. Localization loss will be just MSE between predicted XY offset, square root of width and square root of height and their targets. Here also, we again use the isMax IOU box and object indicator product to capture only the relevant loss terms. The last one is objectness or confidence for background boxes and cells. So all the boxes of cells which do not have an object assigned, and also the boxes of cells that were assigned with an object but which did not have the maximum IOU. The MSE will be same as the objectness term but with target being 0, as these are all background boxes and we want the confidence prediction to be 0 for all of them. To capture loss terms coming only from background boxes, now we'll filter relevant boxes using this 1 minus max IOU object indicator term to give us all the boxes that were not a responsible predictor box. After that, we just add all the losses together, multiplying the localization terms with a weight value of 5, and we also multiply objectness loss from background boxes by 0.5, and at the end, divide by the batch size. So that concludes everything that we need for loss implementation. Let's also quickly look at the training and inference script. The training script has nothing special. It's just going to get the config, instantiate dataset and model. Loss will be the Yolo1 loss module that we just saw. And then the training loop where we compute the loss, backpropagate and update the model. Inference script also has the same template. We first call this method where we get the model loaded with the trained weights and also instantiate the test dataset class. Then we loop over the images and get the model's prediction. And here one thing that we need to take care of is that these predictions will be x offset, y offset and square root of width and height. So we need to convert them to x1 y1 and x2 y2 format, which we do within this method. This is very similar to what we did in the loss module. First reshape the output to be batch size cross S cross 5b plus c. Then we compute these shifts for all the grid cells. Finally, for each grid cell and all B boxes for that grid cell, use the shift and x offset and square root of width prediction to get x1. Similarly for y1, x2 and y2. At the end of this loop, we would have gotten all the B boxes for all the S cross S cells. The class confidence scores for each box are the confidence prediction times the class score for the cell that box belongs to, as that is what the authors define as test time class confidence score. Labels are just the indexes of the class with highest probability prediction for that cell. Once we have converted the output, we'll have some post-processing, like filtering out all the boxes which have low scores, NMS, and after that we'll get our final set of boxes, scores and labels for this image. Post that, I just have some visualization code. Once we train this model, we can see the predictions for different images and even visualize the class probability map that Yolo predicts. The top row images here have predicted boxes, the class label that has maximum score, and its class confidence score. Whereas the bottom row images would be the label of the class that has maximum score for that grid cell. So from the C class probability predictions that our model makes for each grid cell, which class has the maximum score? Note that since this is conditional probability score, we won't have a background class label here. What it basically represents is that out of all the foreground classes, which is the most likely class that the model thinks is present in that cell. So for cells which have distinct features indicating a particular class type, we would usually get the right label. Like for the first image in the center, where people are. These cells have person class label. In the bottom region, where there is a table, it says dining table. But then it also has neighboring cells marked as chair, even though in the image there isn't a chair. My guess is that it's a positional bias coming from the dataset images, that tables usually have chairs around them. I think a similar bias exists for the person class, like cells which clearly don't have any object. For example, the top left corner in the second image, that's marked as person. So that seems like a bias kicking in because of person being the most frequent class label present in the dataset. So if the model must make a foreground label guess, makes sense that it picks the person class. But you should take these labels with a grain of salt. Because after all, it could just be that while that class has the highest score, that score still is something like 0.001, which is not at all meaningful. Here are some other example images and their results. The clear benefit of this one-stage approach is speed. With Yolo v1, the inference speed gets a significant boost as compared to faster RCNN's two-stage approach. But this benefit also comes at some cost. While the model detects objects and their categories well, it lacks in the localization accuracy. The authors provide an analysis of this in the paper by comparing errors from Yolo v1 to errors from fast RCNN, and they find that for Yolo v1, the main source of error is incorrect localizations. Also, because of the constraints that are present on the model, like predicting only 2 boxes per cell and each cell having only one class of object, the model often produces error when working with images consisting of groups of small objects, especially if they are of different classes. The authors mention these and few other limitations in the paper, so do give that section a read if you are interested in it. Alright, that brings us to the end of Yolo v1 video. Hope this one was helpful to you. Do check out the implementation in case you have trouble understanding some low-level details. Thank you so much for watching this video all the way till the end, and do consider subscribing to the channel if you find it helpful.